All right. Hello, everyone. Thank you for attending today's webcast. The topic today will be demand response and connected water heaters in multifamily buildings. My name is Hannah Bastian, and I am with ECEEE, and I'll be the moderator for this session. We'll start the webcast with just a few housekeeping announcements and then quickly move on to our presentations. First and foremost, we want to thank all of our sponsors and ECEEE ally members for their support of the Hot Water Forum and ECEEE. Please use the chat box on the right-hand side of your screen to ask any questions of the presenters. Presenters will not be able to respond to your questions in the chat. As the moderator, I'll gather all the questions and share them to the presenters to answer once all the presentations are complete. If we don't get to your question, please join us for a 20-minute chat and discussion in the Zoom platform immediately following this session. The Zoom link will be posted on the audience screen at the very bottom. Please refrain from using the chat for any dialogue other than asking questions. Be sure to check out all the tabs on the left-hand side of the app. From there, you can network with attendees and program participants, visit sponsor pages, and engage in our game to possibly win a free registration to the 2023 Hot Water Forum in Mission Hills, California. The resources section includes the program and a list of attendees for downloading. Lastly, we want to ask everyone to please help us in planning for future Hot Water Forums by completing the conference's evaluation. Anyone who completes the evaluation and includes a testimonial will receive a $25 discount off their 2023 Hot Water Forum registration. All presentations will be available for on-demand viewing to registered attendees on the Socio platform within a few days and will remain available for viewing until May. Presenters' slides can be found on their page on the program participants section. And now I would like to introduce our distinguished panel of speakers. They are Ryan Green from Nile Water Heating, Mark Frankel from Ecotope, and Tristan Defrondaville from Skycentrics. We'll start with our first speaker, Ryan Green. Ryan Green has been involved in the manufacturing representative side of HVAC and energy efficiency for over 10 years. Most recently, he serves as the Director of Strategic Accounts for Nile Water Heating. He is a member of the Energy Efficiency Building Coalition in Colorado, the Lakewood Sustainability Cooperative, and the Government Affairs Committee Chairperson for the Rocky Mountain ASHRAE chapter. I will now turn it over for Ryan to share his presentation.
Thank you very much, Hannah. Hello, everyone. So yeah, talking today, load shifting opportunities in the domestic hot water world, particularly with multifamily buildings. So one of the first things when we look at multifamily buildings, and especially in the commercial space in general, is we start looking at when we're switching them from their gas sources of domestic hot water into the electrical sources, is we start looking at how these consumers of this energy are billed. And in many different areas across the US, the majority of these commercial buildings are really broken. You can break it down into three main segments. The smallest of which is, your basic service charges on your electric bill. And then you've got your larger pieces, which are your consumption and your demand. The most common one that everybody, it's a common one that is well understood is the consumption. That's how many kilowatts you're consuming over an hour period. And then that's what you're actually getting on your bill is the amount of kilowatt hours that you consumed. The other one that comes up more often and is a little bit less understood, which really can be unfortunate at times because it's a large amount of that bill, is the demand charge. And this is, instead of measured in kilowatt hours, this is measured in kilowatts. And this is that instantaneous power draw by the building, typically measured over a 15-minute window. So if you can imagine, as we're bringing on more electric devices into a building, and more of these devices are not necessarily heat pumps or just a electric resistance source, the problem instantaneously that you can see there is the amount of electricity for the demand is going to be much larger than if we're using a more energy efficient device like a heat pump that has a COP of often upwards of 3.0, where electric resistance is somewhere in the 1. So it really becomes imperative when we're looking at electrifying domestic hot water, as particularly in multifamily, to really start looking at heat pump water heaters, and then using them also combined with these large storage tanks really produces a very good benefit for load shifting opportunities. So when we look at your typical multifamily domestic hot water profile, this graph doesn't really change much as far as how it moves and ebbs and flows throughout the day on a multifamily building. This was an example for a 125 unit apartment complex with approximately 275 occupants and consuming just shy of 7,000 gallons per day of 120-degree hot water. This type of system would be requiring about 1,550 gallons of hot water storage and 326 kBTU of hot water capacity. So what we're seeing on that graph really is there's two distinct peaks. But the other thing that we start to see here is where those peaks aren't, is exactly where we have an abundance of solar production. So if we can find ways to manipulate this load because it is electrically powered, so we can send signals to these devices to be able to shift these loads into the more opportune times. For example, in California, where they're already seeing this phenomenon called the duck curve. What we're starting to see now is this necessity to shift these electrically powered devices into that over generation time, and out of this peak generation time when the solar is starting to ramp down on production. That's where, again, heat pump water heaters combined with a large amount of storage present a really big opportunity to shift those loads around, because multifamily domestic hot water loads are very predictable. They're very peaky. So it's a matter of sizing your storage and the amount of heat pump capacity you have to be able to recover that storage in between your peaks. That is really the name of the game when we're talking load shifting in multifamily with heat pump water heaters. So a lot of the times when we're talking heat pump water heaters, the first one that comes to mind, air source heat pump water heaters. One thing to keep in mind with them, especially when we start looking at load shifting, is that capacity of that unit really varies with ambient temperature, especially when you start getting into some of the colder climates. For example, I'm in Denver, Colorado. Our winter designed ambient somewhere around -10. You can see on the chart below, as that ambient design temperature drops, so does the capable heat pump water heater output capacity. So in colder climates, when we're looking at shifting loads over an annual profile and not just in a summertime profile, it becomes a lot more detailed work needed to look at how much additional heat pumps are going to be required for those colder climates, for those colder design temperatures to meet those capacities required, which sometimes can make systems very large very quickly, depending on the amount of load shifting you're doing on that building. So another opportunity that really, so I come from a lot of water source heat pump systems, ground source heat pump systems, certified geoexchange designer trained. So I've had a lot of experience with water source heat pump systems in buildings, and even district energy systems using a ambient loop, bringing in water source heat pumps. And that's where I think these these types of systems, the water source heat pump water heaters, present an even bigger opportunity for load shifting, especially as we get in larger and larger multifamily properties. Many of these properties already have condenser water systems in them, or already have some type of water source system flowing around in them that can be used as a more favorable source temperature, um, and we get more increased capacity across the band. So now, regardless of our ambient, a water source, a ground source, or even tying into a district ambient loop, you can see the 40, 60, 70, those ambient temperatures are much more favorable throughout the year. So we don't have those swings that we would have in air source. So even in wintertime, when our minimum temperature is even on a ground source at 40 in Denver, it's a lot better than looking at a design temperature at -10 and how much heat pump water heater capacity we're actually needing there. You can even see on the actual design capacities at those design temperatures, we're getting significantly more heat pump water heater capacity because of those warmer source temperatures. So we get a much more controlled and a lot less variable ability to be able to shift loads around. So for looking at going back to that heat pump water heat, or the domestic hot water profile in a multifamily building, and starting to look at how load shifting opportunities here. presented two different profiles. One is just a single load shift. The second is a two-part load shift, one in the morning, one in the afternoon. See how the storage volumes increase as you do more load shifting. And then also the heat pump water heater capacity also increases as you do more load shifting, because you're having to make up the same amount or this larger amount of storage volume in a time between those peaks. So you have to have more capacity, which relates to gallon per hour makeup of that device to recover those storage tanks in those periods. So when we start looking at those different source types, looks like a lot of bars, but what it is the gray is no load shift, blue is the single 4 p.m. to 9 p.m. load shift, and the red is a 6 a.m. to 10 a.m. and a 4 p.m. to 9 p.m. load shift. And what you can see is from San Francisco, 40-degree design temp, down to Denver, negative 10 degree, you're going to need at least 2 or 3, in some cases, air source heat pump water heaters to meet that capacity based on the additional load shifting requirements. But if we go over to a water source system or a ground source system or something on a district ambient loop, we're down to 1 heat pump water heater. So, I come from dealing with a lot of contractors, and, they always said, well, Ryan, at the end of the day, somebody's got to install this stuff. Somebody's got to pay for it. So there's always a conscious effort of how do we reduce that capacity in heat pump water heaters. We're trying to reduce the amount of compressor horsepower by increasing storage volumes. And another methodology of doing that is not necessarily a methodology of reducing compressor horsepower. It's the same compressor horsepower requirement that we're getting here. But what we're doing is we're meeting it with a smaller package and with less overall heat pumps, because we're able to get a warmer source temperature from the water source. So at the end of the day, when we start looking at effectively bringing in load shifting, having these developers be able to implement these systems cost effectively in the most cost effective manners, we'll look at the comparison of a 3 air source system, 2 air source system, or 1 water source system. And you can see the cost comparison really shifts very, very quickly. And then when we start adding in other things like a lot of utilities will do custom rebate programs based on the amount of kilowatt hours and kilowatts reduced by this load shifted system or by the heat pump water heater system versus a baseline electric water heater system in the first place. And those types of rebates can often help to offset this first cost as well. But there's lots of different opportunities here that really, I think, between air source and even more so water source systems, when you really start looking at manipulating what is the source temperature. Because at the end of the day, that's the key thing with heat pump water heaters, is they're really subject to whatever that source is. So the more that we can be in control of that source temperature, the more we have control over load shifting abilities, the more we have control over utility costs, the more we have control over kilowatt demand charges, the more we really gain control over this system. And then when we start breaking this out into these district systems, that's when we start having this simultaneous heating cooling effect. And the net size of these systems can be smaller, because you may have a data center next to a multifamily building that's rejecting heat constantly all year round, and you're just trying to pick that heat up and use it. In which case, that may not be 70-degree condenser water. That may be 90-degree condenser water, an even better source and even more constant to be able to load shift around and reduce our capacity or reduce the amount of cost even further. So lots of opportunities out there in the heat pump water heater world, especially in multifamily. But one thing I often see overlooked in the conversations is water source heat pump water heaters. Definitely don't sleep on them. They're a technology that can bring a lot to the table, particularly in this load shifting conversation. So with that, I'll say thank you all very much. And I appreciate the time today and look forward to any of the questions that come up in the chat.
Awesome. Thanks, Ryan. Actually, can we bring Ryan back? We got one question that I think would probably be easy to answer now. So we had a question from the audience about, is district ambient loop high because of the simultaneous heating and cooling?
Absolutely.
Yeah.
Totally. Okay. You've got multiple different building types. Some are rejecting heat, some are pulling heat, and you just get that synergistic effect of having more buildings onto a thermal ambient loop. Absolutely.
Right. And then there's another follow-up question. What if the simultaneous loads don't coincide well? It seems like district would be far superior.
Absolutely. Anytime you can connect loads thermally is you can start to get those simultaneous loads that don't necessarily coincide. to coincide by connecting those two different building types separately. Otherwise you may have a cooling dominant building right next to a heating dominant building, and they're just, one's rejecting heat and one's taking heat, and you've kind of got a loss of synergy there.
Awesome. Well, thank you very much, Ryan.
Great questions. Thank you all very much.
All right, so now we will move on to our next speaker, which is Mark Frankel. Mark Frankel has been consulting on energy efficiency and sustainable design for over 30 years and has consulted on hundreds of capital projects ranging from single family to large commercial buildings across North America. He is currently the Director of Research and Innovation at Ecotope in Seattle. He has been involved in national coalitions to decarbonize building systems, develop strategies to improve building and grid integration, and in the development of innovative codes and policies. I will now turn it over to Mark to share his presentation.
Thank you, Hannah. Get my presentation up here. Can you guys see my presentation? There we go. Put that in presentation mode. So I appreciate the topics Ryan presented, because that helps me a lot with some of the things I want to talk about. I want to talk about maybe both more detail and a broader perspective on some of the issues around load shift. So Ecotope has been involved in this space for a long time. We consider ourselves experts in central heat pump water heaters. Our approach to the building sector is to electrify everything we can, to design for off, which is our take on efficiency, not just efficiency, but also the most efficient system is one that never comes on. And then when matters, which is it totally matters how you approach building performance with respect to load shape as we move into a cleaner grid. And so those three tenets sort of guide our design work. So Ecotope has been very involved in the deployment of central heat pump water heaters. We've designed many systems that are actively working. We work directly with manufacturers, including Ryan at Nile, on system configuration and custom packaging and putting that together. We're working with utilities and other organizations on performance specifications and standards, how we predict performance and advanced water heating spec, and lots of tools for the industry. We've built our own tools that I'll talk briefly about. We do on-site testing and monitoring to sort of verify both our equipment performance and to track the load shapes, et cetera, better. We're involved in codes and policies, training, and primary research and grid integration. So the reason I point all that out is that we are involved in many aspects of this that informs our sort of holistic approach to this. We work on projects of all scales in multifamily. Multifamily is our specialty. The small projects, oops, sorry, jumped ahead too far. The small projects tend to be simpler deployments. In a small multifamily project, you might use unitary heat pump equipment, which is like upscaled residential equipment, which is combined tank and compressor in one. And that's a pretty simple installation. In the larger systems, we're talking about multiple systems, multiple heat pumps serving a primary heating system, and then a secondary system to provide temperature maintenance. So in this example I'm showing here, we've got single pass systems ganged up to provide the primary storage, and then a multi-pass system to provide temperature maintenance. And those are kept separate because the single pass systems like to see cold water coming in, and the multi-pass systems can add a little bit of heat each time. So that's more suited towards temperature maintenance. And this is important when we start talking about load shift, and I'll talk about that in a minute. So one thing that we've built that a lot of the industry uses is a sizing tool called the EcoSizer that helps people sort of understand the relationship between storage and system type, and it matters what system configuration you have. So this is just a screenshot for part of it. You can put in different apartment size, the number of apartments, apartment type, et cetera. And I want to point out that at the bottom here, there's a load shift tool, and this is V1. So it's a little rough, but you actually can specify as a time period you want to have load shift, and then how much of the load shift you want to get over the course of a year. And I'll talk more about that in building on something Ryan talked about. But if you choose to be 100%, to get 100% of those hours shown for the whole year, it's going to upsize the tank size for you, so to show you how much storage you would need to make it through based on the load shape. And then we also do a lot of simulation of these systems and sort of validate the designs we put in and the measured data we bring, we put it back into our simulation engine to make sure that we're able to predict what's going to happen when you change configurations, which plays into how we do load shape as well. So another thing that we've been working on is trying to make these complicated systems simpler for the industry to understand, going from a custom engineered system where you have to specify every pump and pipe and piece of equipment to sort of a specified built up system where the specifications are a package where the manufacturers can specify which tanks work with them and which pumps to use and which controls, to a plug and play skid where everything comes on a skid ready to install, which makes it much simpler for the design community. And this is a picture of one of our skids. The first one, it's actually not our skid, our design, being installed in Seattle. And Tristan's going to talk more about this project, I think, later. But it's pretty exciting to see this complicated system arrive on a truck and get lifted onto the roof as a single installation. So when we talk about deploying central heat pump water heating systems in multifamily, there's a huge savings potential from this equipment. I mentioned the system where we have single pass heat pumps for the primary and multi-pass for the temperature maintenance. So here's the two pieces, the primary heating and the temperature maintenance. In Seattle, or in the Pacific Northwest, 80% of multifamily buildings are using electric resistance water heat, mostly in individual units, but it's electric resistance. And so there's a huge opportunity to change that over to heat pumps in Seattle. And, obviously you can do it with gas as well, but the savings are substantial compared to electric resistance. So if we put in the system I mentioned with the primary single pass heat pumps and temperature maintenance multi-pass, we get a savings from just deploying this technology of the total building energy of 17%. I can't think of another technology you can deploy in a building that's going to get you 17% with a single technology deployment. So that's a big chunk of savings. And then if we look at the potential for this in the national market, this is a pie chart showing all US energy use for domestic hot water by building type. And what you see is that 4 building types represent over 75% of all domestic hot water load in the US. And the largest one by far is multifamily. Food service and grocery are the next two, and then lodging. Food service and grocery, you could argue, are easiest to serve with unitary equipment, where it's tank and compressor combined. That's a really good application. It's not the only way to do it. Multifamily, I'm mostly talking about built-up systems or component systems, and lodging is probably closely related when you think about load profiles and the way they use water. So it's a big sector. So shifting over to the implications of this on load shape, Ryan already showed a graph of what the load shape looks like for multifamily. And it's actually different. It differentiates between weekday and weekend, and it differentiates between low income or assisted living and market rate. This is a market rate graph from Seattle, and this is monitored data that we collected on one of our projects. And what you see is that Ryan is absolutely right about the shape of the curve, but there's a lot of variability in the peak over the course of different days and different seasons. So for one thing, it's very seasonal. So this is a graph of different days in the year and their delivered water per day. And you can see that the peak, the 95th percentile, is substantially higher than the average, right? And there's also a very seasonal pattern to it, which is a little counterintuitive, but be that as it may, there's a big difference between average and typical load. So if we plot those two things together, what you see is that we have to size for this peak day, which is the red curve, but the average day is the green, right? So there's a big gap between what was usually happening for these systems in terms of how much capacity they need and how much water they have to deliver versus the peak that we've sized for. So if you think about that, inherently in the system, most of the time, there's excess capacity that could be used to manipulate your load shape, right? So Ryan was talking about oversizing to achieve that, and that's absolutely true. If you want to get every single day, like on the slider where I was showing what percentage of the load you want to meet with load shift, then you would conceivably have to oversize the system. But even in the basic system design, because of this spread between average and peak, there is inherently a lot of time when you can do some load shift. So let's look at that specifically based on analysis we've been doing recently at Ecotope for a project in Seattle, not the one Tristan's going to talk about. That we're going to deploy soon. But this is a modeling analysis of an existing project that we designed. So this is the whole building energy use with electric baseline. which is a fairly typical baseline in Seattle in existing buildings. I think the newer buildings are moving more towards gas central, but as I mentioned, 80% of the multifamily buildings in Seattle have electric baseline, electric hot water, and this is what the load shape looks like. And you can see those two big peaks, which if you're a utility person makes you concerned or excited about the potential to reduce them or whatever, because they coincide with the duck curve issues in California and everywhere else. So then if we map over that, the impact on total building energy use, again, total building energy use of putting a heat pump water heater instead of the electric resistance, you can see a really substantial difference. And there's two things going on here. There's the difference in peak and there's a difference in total energy use. So this blue, everything you see that's blue on this graph is the energy saved from deploying the technology, the central heat pump water heater technology to replace electric resistance. And the difference in the height is the peak energy savings during these periods. And you can see it's even bigger in the morning. I'm going to talk more about the afternoon peak because that's one that the local utility in Seattle is focused on for the conversation. So I need you to think about this differently because I'm going to use the same colors just for hot water. So this is a graph similar to the other, but this is just the domestic hot water load. I took out all the other building loads. So the blue, again, is the domestic hot water load for the electric resistance baseline system. The gray is the domestic hot water load for the central heat pump system. And one thing about the design of central heat pump systems, if you compare it to gas, for example, in a gas or an electric boiler central system, the boiler is a big engine and the tank tends to be smaller. So the peak load is in gas especially is meant to be designed with the capacity of the boiler, and the storage tank is meant to make it so the boiler doesn't have to come on every 5 minutes for the lower loads in the day. In the central heat pump water system, it's the exact opposite. The peak is meant to be met by the storage tank, and the heat pump is designed to replenish the storage tank as needed. So what you see in the baseline operation of this system is the heat pump is off in the morning, and then the draw starts in the morning, in the early morning, and it kicks on the heat pump and it runs until it gets through the peak and replenishes the storage, and then it goes off. And then if you're not trying to do load shift, as the afternoon peak starts up, it'll cue the heat pump to refill the tanks, and it'll come on and it'll run until it's done sometime in the late night, and it'll shut off again till morning. So that's the basic pattern for the heat pump as base design. If we deploy load shift, and this white box here is the load shift period for Seattle City Light. If we deploy that, we basically force the heat pump to stay off during this time period, and that's the yellow line. So looking first at this load shift period, instead of letting the heat pump come back on, we're keeping it off until the end of the load shift, and then it comes on and keeps going well into the morning to catch up again when it shuts off when it's refilled the storage tank. And not surprisingly, this trapezoid gray here above the yellow load shift line is approximately the same size as the trapezoid in the morning that we've replaced, because we're not making it more efficient, we're just changing the time period in which the heat pump runs. So the thing I want to point out about this is this blue, again, is the efficiency, right? That's all the total energy savings from deploying the technology. And that, whatever the cost of that is per unit, let's say for the sake of conversation, $1,500 per unit, the cost of the incremental cost to add storage to get the second increment of load shift is a tiny fraction of that. 95% of the deployment cost of this technology is just deploying the technology. And the last 3 to 5% to get this full 100% load shift is the last 3 to 5% more on top of that. So if we could think of a way to bundle the efficiency incentives with the load shift incentives, we could substantially increase the potential load shift riding on the coattails of this major efficiency investment. And there's something there that I haven't worked out yet, but I think that's a real interesting opportunity. So just to cover just a couple more things, the main thing we're focused on in this analysis that I was talking about is using storage capacity to achieve load shift. And again, you have to oversize the storage to achieve 100% guarantee of that load shift period, but there's an inherent amount of load shift capacity just in the design itself. And we could dig in more on what that relationship is. Ryan mentioned that the capacity of the heat pump is part of this because of the recovery. The recovery capability of the heat pump is an important element of load shift. It's not the primary element, but it does impact the need to meet the second. It's really the second afternoon peak that you have to be careful about your recovery capacity. And then another way to achieve load shift is to upsize the temperature that you're storing. It's a little harder to deploy in heat pumps depending on what your ambient temperature is and what your refrigerant is, et cetera. That's not what we looked at here, but that is another opportunity. And then, of course, there's controls issues you have to be able to control for this. And we talk a lot about, is this dispatchable, as if the utility's calling the building and saying, give me load shift today, versus really more of a programmed response to a time of use rate that's really happening every day. And of course, the efficiency value of load reduction is inherent in the technology without any control whatsoever. I have temperature maintenance on here because it's a little bit challenging. I'm not going to talk about that today. There's one more thing I want to show you, and that is, if you remember the 4 sectors I showed you, they're, nationally, for example, multifamily currently is split about 50-50 between electric as a fuel source and gas as a fuel source for hot water. And it's different for the different sectors. Lodging is mostly gas, a little bit of electric, et cetera. If we pile them all up right here, here's the existing hot water fuel for all these sectors. It's not quite mostly, it's pretty even split, more gas and electric, but a little. But because we're deploying such an efficient technology, we can decarbonize the entire sector of this and still have electric savings. So there's a lot of worry that if we move to decarbonization in the building sector, we're adding all this gas load to the electric grid and it's going to increase the electric load. But because of the efficiency of this technology, there's still savings even with the conversion from gas, because that's the blue dot here, is the end energy use of this entire sector if we convert it all to central heat pumps. So I will stop there. Thank you so much for your time, and I will entertain questions now or later.
Awesome. Thank you. I think we have one question, but I think we can save it for the end and move forward. So thank you, Mark. So our next presenter today, and our final one, will be Tristan Defrondaville. He has more than 20 years experience in the software and hardware engineering management. He's the founder and president of SkyCentric, a leader in open standards smart building solutions that include the CTA 2045 EcoPort, OpenADR, Voltron, and Linux. I will now pass it over for Tristan to give his presentation.
Hello, everybody, and thank you. We're just lining up the presentation here. I will make sure I'm in presentation mode, and thank you very much. And is it correct, Hannah?
Yeah, I don't know if you can still hear me, but looks...
No.
Oh, no, actually, you need to switch it.
That's what I thought. Oh, yeah, it's because of this. Sorry. I tried something that I shouldn't have done, but here we go. How's that?
There you go. That looks great.
All right, great. So briefly about SkyCentric, as Hannah said, we're a leader in EcoPort modules, Wi-Fi, and we've released a cellular module, which is pretty exciting. And we provide OpenADR solutions, both to OEMs, and we have a certified cloud that helps them become a connected device. So I'm going to be talking and following on what Ryan and Mark have said. And frankly, the experience that I have is a little bit more on air-sourced heat pumps, so it was fascinating to hear about Ryan's sort of ambient loops and ground source, etc. But I'm going to be talking about mostly air-sourced heat pump choices. So these are 2 projects that we've done, and they represent a broad swath of multifamily. So there's high-rise and there's garden style. That high-rise building's in Seattle, the garden style's in Hawaii. So when you're looking at these options, the next thing is what kind of water heating generally exists. So garden style, a little bit harder to do the kind of central system water heating that Mark was talking about, and maybe Ryan as well. Garden style generally has either water heaters that are inside each apartment, or in this case, it's in Hawaii, so it was pretty easy because the ambient temperatures are temperate. They tend to have water heaters on the outside of the apartment in Hawaii, but sort of on the inside of the apartment in other states. And typically you're finding gas water heaters in the garden style, electric water heaters, and then low boys so that they can fit into the apartment and a little bit smaller. And of course, heat pumps tend to be bigger than either the gas or the electric units, and if they're low boys, you're maybe going to have a hard time putting in the heat pumps in the garden style. On the other hand, high-rise tend to be located inside if they're unitary, kind of the same issues I just talked about. But if they're outside, then I'm trying to hide this thing that's in my way. But if they're outside, then the central systems are kind of outside or inside. They're often in parking garages, in a corner of the parking garage, and they're gas or electric, obviously not low boy. So let's talk a little bit about the issues that we've seen as we talk to owners of residential buildings, multifamily. So on the garden style, you have quite a number of issues as you try and move to heat pump. Outside is easier, as in this Hawaii example. Inside, a little trickier, right? There's more noise. There's not always power available. So that means, especially if they were gas water heaters, obviously if they were electric, there's power available, 240 volts. But if they were gas, there is not power, certainly not 240 volts. So then you have to have an electrician come in and bring power to the unit. And sometimes that increases the power required at the service entry of the entire utility, and that's a big cost as well. Then there's space issues. I talked a little bit about that. And finally, if you're inside the apartment during the summer, I'm sure the tenants are happy to get some cold, dry air as the exhaust, but in the winter, they might be concerned about the heating bill. Now, NEA has done some studies and shown that the heating impact is fairly negligible, even in places like Washington and Oregon. And then finally, the condensate. There's a little bit of condensate line water that comes from the process, a little bit like was historically on those window box air conditioners that would drip on you as you walk by under them. And that also needs to be installed. So if it's all inside an apartment, we've seen these water heaters, typically gas or electric, mostly electric, I bet. But they tend to be in a place where the noise could be impactful. So all of these issues make an owner of a multifamily apartment building be a little bit nervous about changing over. Now, they certainly are attracted by the economics. They're attracted by the general savings. But if the water heater is inside the apartment, it's often sub-metered. And that means that the apartment tenant is paying the bill. And at that point, they're sort of like, doesn't affect me that much. Finally, connectivity when it's inside the apartment. If it's Wi-Fi, garden style, every apartment wants to have their own Wi-Fi. So multifamily and Wi-Fi connectivity to an individual water heater is really tricky. And I'm just going to move on to the high rise and say, hey, connectivity is easier, a lot easier, right? There's only one location. When you're moving to the heat pump, if it's in the corner of a garage, sometimes that storage that Mark talked about, you need more storage typically, and that may be harder to put in, although you may be removing some of the prior equipment, but a lot of times you want to leave the prior equipment in. I'll be talking about that when I get into a detailed retrofit. And then finally, there's still the power issues that 240 volt might not be present if it was gas. Okay, so let's review briefly the central system retrofit benefits, because central system, we believe, is really the holy grail that we should really quickly be doing around the country. Number one, the installation is a lot less impactful to tenants. I mean, when we've worked with garden style or anywhere where the water heater's inside the actual apartment, then we know that about 10% of the apartments become free once a year for a certain amount of time. And obviously the landlord prefers to do it when the tenant's not there, when in between tenants, so to speak. But other than that, a central system can be done with almost no impact to tenants. So that's a benefit. There's less noise in the apartment because it's a central system. It's easier to bring power to the location. You only have to bring it to one spot. There's fewer space issues, although a few. This, as Mark showed, is being installed on a rooftop, so that wasn't prevented by the space inside a garage. And finally, there's no submetering issues, right? If you have a central system, it's typically been run by the landlord. And so if you think about it, that means the landlord is already finding a way to include inside the rent this global water heater charge. And so he's motivated to save the money. When if the tenant is paying the bill, there's a lot less motivation. So I'm going to talk a little bit about the details of these Hawaii installation and the incentives, because it always helps when you're going to landlords to talk about the incentives that are possible. So Hawaii has done something fairly innovative because they have a lot of solar. In Hawaii, there's a state incentive that if you control a water heater with the sun, then you get a $2,000 incentive per water heater. Now, that historically has meant solar on the roof, either in the form of PV sending electricity to the water heater, or in the old days, you may all recall that we had, black water bags up on the roof that were being heated, and those sounded great in the 70s and 80s. My parents had one, but they tended to leak and have other problems, so they have not been that popular over time. But what it meant is in this particular installation that you're seeing, the company we worked with is a company that provides batteries plus solar, right? Solar plus batteries, solar plus storage, a kind of classic that you've heard about. But their innovation is that over 134 apartments, instead of every one of these units with 6 apartments that's a separate building, as you see right here, they have a DC power bus that allows the entire system, all 134 units, to share the same battery plus solar. So that means that if 6 people are not in the apartments in one building and that building's empty and normally wouldn't be using any electricity that day, all of the solar plus battery can shift over to a building that's got a lot of usage going on. So that's where you get this number, 25% more energy delivered with 50% fewer batteries. However, because they got the $2,000 per water heater incentive, plus the ability to control our water, the water heaters through a CTA 2045 EcoPort, they were able to reduce that battery by even another 10%. So it's just kind of an exciting way to handle multifamily in Hawaii that I think anywhere where there's a lot of sun should be encouraged to do the same thing. Okay, then in California, these are the incentives. I'm not going to go over the whole chart, but the big one that's finally been released is the tech incentive in California. Right now, it's providing about $3,000 per apartment, or per door, as it's sometimes called in the multifamily space. And it's doing that $3,000 per apartment, whether you're doing central system or unitary residential. So that's exciting. It covers a lot of the cost of a central system or swapping out. Frankly, I think it covers the central system a little easier. The problem, as I said, with swapping out unitary is if you have to, a lot of them in California at least are gas, right? So that they have to bring in electricity and increase the service. Now, if you want to take multifamily water heating to scale, I have 2 more parts of my presentation. I have the commercial heat pump incentives that we're trying to do with AWHI and a subcommittee that I'll go over briefly, and then the details of the power of multifamily savings in high rise and a central system. So our goal with commercial heat pump incentives was to provide a test plan for UL and Intertech to have a metric that they could test a heat pump water heater system, mostly the compressor, for utility incentives. And the test plan should deliver a metric M, variable according to size of the heat pump compressor, volume of storage, and ability to shift the load. So that would make sense, right? As Mark showed, if you can shift the load with a little 3 to 5% more storage, you should get a better utility incentive. So some of the things that we're doing, which will be of interest to folks, is number 1, you have to have a mixing valve. Now that's easy. Most multifamily does that. Number 2, we always want the system to be able to deliver some power measurement so that, the utilities can know and the aggregators can know when it's on or off. So that's being done. we went to plus or minus 20%. Most systems are going to be able to do better than that, but that's at least a minimum. And then this is a big difference over all the other things you've heard about from Energy Star, Title 24, JA13, et cetera. We're going to mandate that it's connected at install. These central systems use much more electricity. There's so much grid value to them, like typically 20 kilowatts and more versus the 4.5 kilowatts of an electric resistance or the 0.86 kilowatts of a heat pump. So it's really important to have these connected at install, ready to go. The grid signals can be sent immediately. The system can deliver data immediately, and no follow-up visits are needed to make the system be grid interactive. The system should be able to turn off any resistance element in the system. Now, that means, as I'm going to describe in detail the next project, when there's legacy electric resistance tanks, the system control has to be able to, as the receiver of the grid signal, have at least one method to communicate to external electric resistance equipment and turn it off. So that's kind of an exciting thing we've put in. And we strongly encourage utilities and aggregators to incentivize this installation incentive based on the metric M that UL and Intertech will provide, and then a performance incentive 6 to 12 months later based on actual performance in the field. So that's what we're rolling out to encourage incentives to really do this market transformation and this world transformation that we need as we migrate to using less carbon in our energy. So here's the high-rise example. It's in Bayview, as Mark said. It's got about 100 units, 100 occupants. And the important thing is, prior to doing the retrofit, it was 102 kilowatts of electric resistance elements. So what did they do? We installed that rooftop skid. And what you'll see is that 102 kilowatts, 6 Rheem electric water heaters, went to 19 kilowatts of the heat pump system. So that's what, about a fifth. And then we kept the old 102 kilowatts for backup. Now, it turned out to be important because it turned out that a pump in the system had trouble. And for about 2 months, we had to run all on the backup, but that was fine. And I guess it also meant that, oh, well, it was a new roof-mounted assembly. That's why it didn't impact the space. Okay. Then I'll come back to that in a sec. Did I miss a slide? Oh, okay. So let me tell you a little bit about the shift. So the shift capability of this system is such that the 19 kilowatts is actually a max. When it's really operating at its design feature, remember how Mark said that the yearly peak is rare, right? It's on the coldest day of the winter with the most usage, better be a weekday. And that's when you expect some of the electric resistance maybe to come on, and you're maybe using the 19 kilowatts. But on an average day, you're using 10 kilowatts of the heat pump. And your backup resistance is really designed to never come on. So that 102 kilowatts is never coming on. And instead of 102 kilowatts, you're using 10 kilowatts. And you might be using it for a little bit longer. And the system is essentially easily designed to coast in totally off mode during the morning peak. And as Mark said, it's a little trickier for the evening peak, but with a little 3 to 5% extra storage design, when you're doing this big install, that means that there's almost no cost to add that extra storage. So these systems are designed to stay off for about 8 hours a day, and that matches a morning peak 2 to 3 hours, an evening peak 5 hours. It's really a beautiful setup, and I just want to finish with what we did is we worked with Seattle City Light and Ecotope for all the data export. We provided OpenADR and CTA 2045 to this system as a way to receive the grid signals. This is a very censored system. We have about 70 data points coming from it. Future systems will have fewer data points, but this is really showing how it's the bleeding edge of the market. But Mitsubishi and others, I'm sure Nile, all expect that with incentives and with these economic value propositions that are being shown to the landlords, and with the utilities seeing both the energy efficiency and the load shift capable, that these are really going to be rolling out in high volumes, and they'll need open ADR and CTA 2045 eco ports to receive the signals by Wi-Fi or cellular. And in general, it can afford cellular because it's such a higher electric load. So I'm just leaving this slide up as I finish so that you remember why central systems are so great, and my contact information, and thank you for your time.
Awesome. Thank you so much, Tristan. That's really cool to see that project and how much energy you guys are saving. I guess we can bring everyone back into the room if that's okay. We got a few questions in the chat, and I wanted to open this up, I guess, to anyone. So what is the equipment, devices, and controls that you need for load shifting for these systems?
I'll start, and then Tristan maybe will have something to add. The system inherently has a lot of capabilities. In Washington and California, and I think Oregon, the CTA 2045 port is required by law. There's been some delay because of supply chain issues in the full implementation, but that's the receiver port that you can plug the device into and control, and there's logic involved in that. And while I have the stage, I'm just going to mention one thing. Tristan, when I mentioned the 5% cost increment, that's the relative cost of increasing storage compared to the entire system cost. It's not the amount that you increase the storage by.
Right. Thanks. Yeah.
Okay. Tristan, you want to add anything about what it takes equipment-wise?
Yeah. In terms of, as Mark said, right, typically a little bit of extra storage cost is needed, so small that it's really worth making sure it's in there. And then communication, and that AWHI subcommittee initiative is essentially in the same way that the EcoPort sort of commands have enabled Washington to pass the law, and California Title 24 JA13 and others, with the confidence that the water heater is going to get the signals that are useful to the grid. The same thing is happening here with commercial systems, that we're making sure that these systems are designed with the minimum communication ability to get good signals, not only for the shift that we want to do every day, as Mark said, but really for the future, where the amount of shift in the hours, time of use is, again, everybody who's heard me say, it's a blunt instrument, right? During fire season, when gas or power plants or coal power plants are suddenly being shut down or having a problem, like in Texas, it's huge to be able to send a 24-hour ahead or even a real-time price signal. And that's really what we're building into these connectivity standards, especially in commercial.
And then I guess thermostatic mixing valves, is that another thing you would lump in as like an equipment you want to add?
You know, this is where Ryan and Mark can answer. I'm only assuming, that it's generally always in a commercial system anyway. But what do you guys say?
We always specify those. That's a better way to go than any other option.
And would recommend electronic over just a regular thermostatic as well. Having that ability to get the monitoring and to the controllability of the electronic is a huge benefit. Yep.
And Ryan, what's the difference in cost? Because I know the thermostatic is about, $200 installed or something, but
I know it varies from manufacturer to manufacturer. There is an incremental cost increase to go that route. But I think when we start looking at the overall system cost of the domestic hot water system, it's going to be a negligible drop in the water there.
Right.
Yeah, I guess that was a question that I was going to have for you guys. How much extra cost does adding this grid connectivity add to the systems? And I'm thinking of that from the perspective of a utility is going to incentivize this kind of stuff. What's that incentive level that you think would be good enough to push the market to really adopt them?
Well, what's magical is that by the time the OEMs, both in unitary with this port, just having the port, so it's relatively low cost for them. I mean, they have distribution issues. It's a commodity white good, but the port itself is about $2 worth of plastics and some wiring, right?
Yeah.
They'll complain that it's more, but and then because look, they have to put a CPU that can handle it, but the minute they're putting Wi-Fi in, so the point is fairly negligible. And then our cellular module, I mean, these are low volumes so far. We haven't done it, but we're charging $180 for a cellular module that can connect to the whole system. So once the system can receive the signals, the connectivity piece compared to the cost of the system in commercial is super cheap.
And I'll just add, that there's an inherent amount of load shift capable just by the nature of the system, as I showed. If you want to make sure you can get it every single day, no matter what, there's like, you get 80% for no cost or 75% no cost and 90% for 10% more, whatever, storage. If you want to be absolutely certain, you really have to substantially increase the storage volume. So it's sort of a question to the utilities. Is it really worth those last 5 hours in the year, or not?
Yeah.
But it's still the small piece of the equation. The system deployment is way more expensive than upsizing storage tanks.
Yeah, absolutely. Yeah, I mean, just in general, out in, when we're talking to developers and things like that, they've always got the metric of, if it doesn't pay back in 5 years, then it's usually not a pursuable thing unless it's code legislated or there's some other type of, stick behind that carrot. So I think, when we start looking at incentive programs and things like that, it's getting as close to that 5-year mark that the developers is really going to get their ears to perk up and say, okay, this makes sense to me now because it's actually going to, make sense in my pro forma when I'm putting it together to build this building here.
Yeah.
The one other caution I would say is, and this is true in the residential scale as well, but if your load shift period triggers the electric resistance element as the backup plan, that's the wrong direction, right? So you got to be really careful that you have a strategy to not get to the point where you're in desperation and kicking on electric resistance in your shift period.
Okay, so we have a follow-up question kind of on that. Who is responsible for installing the demand controls? Is that a plumber's work, an electrician's work? Like what, I guess the broader question is like, what is the workforce for this kind of?
Yeah, so good question. I can start a little bit with that. So the controls box typically is going to come with the OEM of the processor, the compressor. In the case of a skid, it's really nice because the skid is a little bit more complicated and the skid has some kind of a control box. In fact, I should have shown everybody the picture. There's really a box there and it had a smarts for, a box of a CPU controlling the skid. Therefore, it could control that. And it was pretty easy to install. And then obviously a little connectivity module or a cellular connection is typically easy as well. So that's the advantage of a skid. On the built up systems, do you guys have any idea how that's going to work?
The model that we're thinking is that the plug is inherent, the CTA 2045 is spec'd, and then the utility, depending on what technology they're going to deploy, whether it's Wi-Fi or cellular or whatever, that's a plug-in module that communicates. And it might be time of use rate, it might be a radio signal, whatever. But it needs to be commissioned. I think that needs to be factored in, make sure it's working. But it's, the dream is you just walk in with a device, plug it in, and walk away, plug and play, right?
Go ahead, Ryan.
From the manufacturer side, I know the CTA 2045 port is going to be a standard offering on most of the heat pumps. So, from that side of it, it'll be negligible. Like you said, it's already going to be part of the heat pump water heater system cost as well. So it's a matter of making sure that when they're designing the system and the documents go out, that's in the sequence of operations to be commissioned on design day. That's, as Mark was saying there, that's the most important part is, designing the system is one thing, but setting it up to operate as designed is the other.
I think there's one more thing to say. I know we're running out of time. I'm curious, when you have a gang of sort of 8 compressors, they might each have the port on them, but then you don't want to put a cellular module on each one, right? So the question is, will the OEMs be able to put a cellular module on the one to receive grid signals, but somehow make sure that the other 7 are paying attention to the one? That'll be an interesting question.
It's like a dummy slave that chains down from the one point of connection, right?
Yeah.
Awesome. Well, we're right at time, but we still have our Zoom Q&A, so I think we can end here and then I'll meet up in the Zoom meeting. Thank you, everyone.
Thank you.